Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the final one in the first series on centre of mass and moments, and it focuses on the use of integration for solids of revolution. Let's begin right away with the problem. We've got here a curve y equals root 9 minus x. The shape of the curve's here, and that's rotated about the x-axis to give a solid of revolution. Now, assuming that that's of uniform density, we want to find the position of the centre of mass. Now, what's obvious from the beginning is that by symmetry the centre of mass will lie on the x-axis. So unlike the two-dimensional situations, the three-dimensional ones are essentially simpler as a rule. So our first point is that the y-coordinate of the centre of mass is 0. We'll focus on calculating the x-coordinate now. Well, as with the area, we do it by dividing the shape up into elements. In this case, the element will be a disk. So it's a thin disk of thickness delta x, and we're going in the end to add lots of such disks up and let delta x tend to 0, which will give us a calculus limit and hence an integral. So it's at a distance x from the origin, it's got radius y, and its width is delta x. That allows us to work out its volume and make the appropriate substitution of a particle for a mass. That's a mass distribution. So it's approximately a cylindrical element, and its volume is pi y squared delta x. So if we have a volume density, which we'll usually denote by k, we've got the mass, and so we can, by considering it as a disk, we can say that its centre of mass is at the centre, and we can replace the disk by a particle on the axis. And so each of those disks is a particle, and we end up with a line of particles, which we can analyse in the ways we've done before. So let's have a look then at what we do first with the mass, given that we've introduced the mass per unit volume, k by pi y squared delta x. We add lots of those elements up and let delta x tend to 0. That will give us an integral, which in this case goes between 0 and 9, and it's of k pi y squared dx, and in this case we know that y is equal to the square root of 9 minus x, so that's the expression that we can substitute to evaluate the integral. So it's the integral from 0 to 9 of k pi times 9 minus x dx. Well, the k and the pi are constant factors, so let's then put them out at the front. And so we're going to integrate 9 minus x, giving us just 9x and minus x squared over 2 between 0 and 9. So that's k pi times 81 minus 81 over 2. That's the upper limit, but the lower limit with the 0 in it gives us nothing. So 81 minus 81 over 2 is just 81 over 2. So 81 k pi over 2. Now that's essentially a volume calculation for a solid of revolution with the factor k in, which turns the volume into a mass. So that's the total mass for the solid that we're considering. Now you'll remember that if you're calculating the centre of mass, you do it by saying the total mass times the centre of mass coordinate is equal to the sum of the elemental contributions to the moment. So now we need to ask, having got the mass of the element, what's its moment? Now if we replace the disk by a particle at its centre of mass, we're essentially saying what's the moment of a particle with mass, that expression, at a distance x from the y-axis. So that will be k pi y squared x times delta x, And before I write the delta x, I'll say that we're going to add all those up and let delta x tend to 0 so that it becomes an integral between 0 and 9 of ky squared x dx. So that's what we're going to calculate next. So we've got the total mass, and now we've moved on to the total moment, which is the expression there, and we know that y squared is equal to 9 minus x. So if we substitute in, we have the integral from 0 to 9 again of k pi times 9 minus x times an extra x dx. Well, once again, the k pi is just a factor, so it's the integral from 0 to 9, slightly more complicated this time because it's 9x minus x squared. So that gives us the k pi as always, and then 9x squared over 2 minus x cubed over 3. And that's evaluated between 0 and 9. So for 9x squared and x cubed, we're going to be evaluating 9 cubed, which is 729. So 729 981s in fact, isn't it? So that's 729 k pi, and then a half minus a third, and that's from the upper limit. The lower limit contributes nothing. So that's 729 k pi. Now a half minus a third is 3/6 minus 2/6, so that's just a sixth. So that will allow us to cancel down. Not quite entirely, we can just cancel the 3s, so there's a 2 3s make 6, 2 3s make 6, 4 3s make 12, and 3 3s make 9, so we end up with 243 k pi over 2. 243 k pi over 2. Now let's recap what we've done so that we don't lose track of these big expressions. There's our picture with the element. That was the mass, and we took the centre of mass at the centre of that disk, thin disk. We used the moment element in order to make the contribution to the integral. We ended up with k pi y squared x dx integrated. So that gave us the total moment at the bottom, that expression at the bottom. That's what we've just worked out. So we now know the total moment, we know the total mass. So the usual thing is that we've worked out both these integrals, but we're making essentially that equation, so it will be x bar times the answer we got to start with, which if we go back a couple of slides is 81 k pi over 2. 81 k pi over 2. 81 k pi over 2 times x bar is equal to, and the other one was 243 k pi also over 2. If you don't believe me, we'll check back briefly. 243 k pi over 2. So that gives us that calculation to carry out. I'll go back one. Are we working out now what x bar is from that? Well, it's pretty obviously 3, isn't it? Because we can lose the k pi's on both sides and the 2's, and it's 243 over 3. So we get x bar equals 3. We do all our calculations just as we've done, and we get 3. So there's not much more to it than that, just a little more neatly done there. You can see that once you've got the idea of the basic shape, that it's the moments on the top and the mass on the bottom, you can cut a lot of time by expressing those two integrals simply as a ratio. And this is generally yx and y squared x, and this is just y, and that will be a general rule. So as I say, we've got 3 there from the numbers that we got. So the centre of mass is at 3, 0, a distance 3 from the circular end along the line of symmetry. Well, let's sum that up. It's very much a repeat of what was done for areas with the usually occurring simplification that you don't need to work out one of the coordinates because it will be obvious from symmetry. So to get at the centre of mass of a uniform volume of revolution, we can do it by integration. And for a solid of revolution about the x-axis, we have the ratio x bar is the pi y squared x integral over the pi y squared integral. The k's will usually cancel out as we've taken it out there, and that's because it occurs on both sides of the term. We've put it there really to make the terms dimensionally correct. So that brings to an end that particular presentation. I hope that seems a good bit simpler than earlier ones. It's very much a repeat in the 3D context with that additional simplification that you can use symmetry. So that brings this first series on the centre of mass and moments to an end. So I look forward to resuming with you on the second series.